Hey everyone, so this is a behind the scenes video, but it'll be for public release on the GN Steve channel. I'm going to show you some of the stuff I've been working on lately. I've been cycling through coolers on our cooler test bench over here. So this has gotten a lot of use. I just pulled the Noctua cooler off of there, but this I've been doing 3800X and 3950X. CPUs of varying overclocks, varying power levels. We current clamp it to make sure we get the exact power going in every time, all that stuff. It's all described in a separate video on the main channel. But the other thing I've been setting up is the dummy heater. So that's over here. This, interestingly, also required me learning how to set up our fan testing stuff. So we kind of, in terms of just like training and education, learning how to use the tools, knocks two things out at once. But I'm going to set this up and show you kind of how it works. All this stuff was really expensive in both time and actual cost. It's worth it because I know it'll help us do validation in a much faster way. I'll explain the dummy heater and all in a separate main channel video, but it's not replacing our main test bench for cooler reviews. It is supplementing it. So we'll get two sets of numbers. The cool thing with a dummy heater is that I can scale up the temperature however I want because we just attach it to a synthetic load. This is loud. So we attach it to a power supply with a bunch of power modules on it, and we can set the amount of power that's going in to the dummy heater via these cables, which Patrick has modified to put sense lines into. That's what this Ethernet wiring, the leftovers, is from. That's a sense line. So I'm going to try not to go too much detail on this because I do want to leave some for a main channel video once it's all ready. But I'm going to give you guys on the secondary channel an inside look at it before we get there. So anyway, long story short is that we designed this dummy heater, worked with a company to manufacture it. It has a Ryzen IHS on it, like exactly a Ryzen IHS, except there's a hole milled in the top, and that hole has a thermocouple in it. So there's a thermocouple that comes over here, then we plug this into a thermocouple reader, and we can take ambient, and then we can take the case temperature. It is not directly comparable to a CPU because we're not taking T-die from this because there is no die. So this is just resistors hooked up to power. Ultimately, a CPU is just power. When you're measuring the cooling, CPU coolers, when you're reviewing them, all you care about is how much power is going into the CPU, how much heat's coming out, and you measure that in the form of temperature typically. So yeah, so we did basically designed and worked with a company that engineered the CPU, synthetic CPU for the dummy heater. We hook that up via cables. We can push into different dies. So we've got 3 chiplets on this thing, which basically working with them, I asked them to position the resistors in specific places so that we can heat up where chiplet 1 is, chiplet 2 is, chiplet 3 is, and chiplet 3 being the IO die. So they're capable of doing 130 watts on the 2 main CPU chiplet fakes. They're synthesis chiplets. And then the third one, we're capable of doing up to 50 watts in the IO die. And I determined those numbers by measuring the processor power consumption in different places. So yeah, that's all that stuff. There's a lot I need to do on this. Right now I'm basically using it for internal validation, and then we'll eventually use it for external public numbers. But we're no longer letting stuff like this hold us up on publishing. So we're going to be publishing with the test bench we have on the other side of the room, which I'm really happy with those results now. I've gotten them really solid and repeatable down to within a degree, basically. It's crazy. And then we'll add this stuff later. But this will allow us to do more stuff like testing thermal interface materials. You can't really do that reliably on a bench platform or real computer because there are too many variables. But with this, where it's only power, there's no motherboard or BIOS or any other BS to screw with it. This is easy to do that kind of testing. So let me walk you through the tools and the setup. I'm going to throw a cooler on here really quickly, and then we can show the rest of this stuff. So I'm just going to throw a Noctua cooler up and get this thing going, but this will take a minute. All right, so I set up the Noctua cooler on here. This isn't really intended to be like an actual benchmark test. There's no numbers we're going to take away from this other than showing you how it all works. But that's hooked up. Thermocouple Reader is hooked up to the thermocouple. I have a tachometer marker on here so we can take the fan speeds. And then this is our custom PCB that we've made to do the fan RPM control. So, actually, let me switch these. This is, it's got 2 fan headers on it. So we have like these 2 4-pin headers. I just bought all the parts on like Mauser or DigiKey or something. And we're hooked up to an oscilloscope. And that'll provide some of the power to and from the computer anyway. The oscilloscope's going to connect by USB to the laptop. This is all because other fan controllers aren't really that accurate. So like the Corsair ones are pretty good, the Commander Pros, but they're not perfect. And I can get a whole lot more out of this. I can get more accurate readings with everything and control everything much more easily. You can automate stuff more easily if you want to. This is a benchtop power supply, one of the many that we have here. So this one only provides 12 volt and it's going to the fans. And we need 12 volt for PWM fans. And then we just change the wave generation if we want to reduce or increase the fan RPM. So that'll get our fans powered. And then I need to go into software and actually tell it, oh wait. I need to go into software and actually tell it what to do. So we can turn on the scope, the wave gen, and we've got fan spinning now, and the supplies. And if I go to scope, you'll see the square wave for the fans. We can take the frequency that the fans are, that the sensor's being read at, and we can multiply that to get the RPM. So if we take, is it going to be times 30? Yeah. So it's going to be times 30 because of how many pulses per revolution are being sent. And then we can take this, which is a physical tachometer, laser tachometer, and I can validate the speed. So we're reading about 1520 RPM or so, 1520 on this. And then the quick calculation on the computer there is reading about 1500 RPM. And if I added in all the 3 decimal points, it'd probably be a bit higher than that. So we're pretty much dead on here. So that helps us validate the speeds. I've got the leads are all hooked up here. So got ground going to ground on the PCB, hot's going to hot, and then I need to tape these over eventually to protect them from shorting into each other or anything. So we've got, the fans are powered. We don't need a computer for this, other than I guess oscilloscope and laptop, but this is much better. And then I can control the fans more directly, and we get more accuracy that way. So that's going. I can set up the temperature reading. So this will be our replacement for typically like hardware info. We're using all physical hardware tools instead of software. So this is much better. And we get an ambient temperature at intake. The room is not at our, if I were actually running tests right now, I'd bring the room temperature down a little bit. We're running a little bit hotter right now because there's CPU tests going on in here. But we're not doing a real benchmark, so it's okay. I would drop this to about 21, 22 otherwise. So power supply, this thing has 3 modules in it. I have a 115 volt for the highest power. I think the amperage on that's 3. So it's 115 volt, 3 amps. And then we have 2 that are 60 volts and 5 amps, I think. So I use the 115 volt to power, like if I use the Intel dummy heater we made, I would use it to power that because we could push that up to like, I don't know, a couple, several hundred watts, I guess, whatever it's built for. But so yeah, that's the basics for the kind of the power supply specs. I can go through here, configure how much power we want to push into the dummy heater, and we can also program stuff. I can hook this up to Ethernet and run automation through the network, so that's pretty cool. We just write a script for it, tell it what to do, and it would just start executing the test, leave a cooldown period, all that stuff. Yeah, that's going to be the basics on how that's set up. So let me get a heat load on here so we can do a demonstration. I'm just going to set, we'll use channel 3. Channel 3, I'll set it to, I don't know, like 30 volts maybe. So 30 volts. And then, yeah, 3 amps. Okay, and then on. Oh, I mistyped the first one. 30. Okay, so now we're running at about 30 volts-ish. It's pretty accurate. So Patrick soldered in the sense lines on those cables, so we get a sense at the end of the cable and at the start of the cable. That way the mainframe here can accurately account for the delta and any voltage drop across the line. And ignore the property of the US government sticker. We didn't steal that, I promise. And let's see, so that's going to come out to 1.710. So that's about 51 watts right now. Let's go ahead and power. We don't have heater 2 plugged in, so let's power heater 1 as well. And we'll do I don't know, 15 volts, and we'll tell it to just do as much current as it can on. So that one is going to, that's not quite 20 watts. Let's do, oh no, it is. That's 20 watts. Okay. So we've got 70 watts going into there now. Let's go ahead and connect that second heater. Did I turn it on? Yes. We're going to connect the second heater. Some of this stuff's a little dangerous, but it's not like you can buy it, so there's not really any point to me going over safety procedures. Just know that I'll be fine. I'm the only one working with it. So channel 2. And channel 2, we'll go ahead and let's just set this one to, I don't know, about the same as the other one. So I want 50 watts out of this one. What does that give us? 30.004-ish times 1.659 is going to be 49.8. So we're at about 120 watts now. So this would be about what like a 3950X would do. It'd be about 10 watts higher, but 3950X running Blender is kind of what this would be simulating right now. We've got 3 dies hooked up. They're not literally silicon dies, but there's, you know, analogs for them. And those are all hooked up, push about 120 watts into the plate. If you look at our thermocouple reader now, the smaller number in the bottom left, that is the temperature of the sensor that's milled into the IHS. And then ambient is about 24 for the intake. And I should note too, the side venting. So this thing here, even though you might be looking at it going like, wait a minute, there's exhaust there. This is a different unit, so we don't use this one actively. This is part of the Sun Moon solution for power supply testing, so that's not actually in use. And this is serving as intake, not as exhaust, so it's irrelevant. The exhaust comes out the back, and we can move the dummy heater around as needed. But anyway, so the temperature currently with 120 watts going into it is 33 degrees Celsius in a room ambient of about 25. I can check my notes if I had them next to me, but ultimately what we do is we log a delta T over ambient, so this value is going to be a little under 10 degrees. Yeah, like 8 something, 9 degrees difference between the two, and then we'd swap the whatever we're testing, interface, cooler, power load, whatever. You could test the same cooler with multiple power loads. So this is something that's really cool with this, where we'll show this in the Corsair A500 review. It might be up already, but that particular cooler scales really poorly with power load increases. I did that with the physical bench. It takes forever to do that because you're changing CPUs. You have to dial in the overclock. You have to revalidate that the motherboard's not screwing you over with weird changes. This thing, all I have to do is type in a number. So like, let it run for half an hour. Write down the values. I mean, I log them actively every millisecond. We do it through a spreadsheet, but effectively write down the numbers, and then let it cool down. Change the heat load. So we could do simulate 65 watt single chiplet CPU die, single chiplet IO die CPU. We could scale up to 95 watts, 120 watts, 150, 210. We could do an overclock 3950X simulation at 300 watts if we want to. And we could leave the same CPU cooler on there for the whole thing and show how does this specific cooler scale and its ability to handle or soak that heat load. And just keeping in mind that the deltas will be a lot lower. So like for a 120 watt heat load here, we're seeing a delta of about, now it's still climbing because it takes time, but it's at about 11 degrees Celsius now. So I think if I remember correctly, this one settles at 12. It might go to 14, but off the top of my head. So let's say 12 degrees Celsius is the number. If I test that on the computer with the same heat load, it's probably going to be something more like, it's probably about 52 degrees Celsius, delta T over ambient, but that's T die, that's inside of the silicon. So there, you can't compare this number to that number directly, but you can compare the hierarchy directly. So if I do the same power tests here as I do with a real CPU, the numbers in an absolute sense will be different, but the hierarchy, the ranking of them will be about the same. And that's pretty cool. So that allows us to really rapidly prototype ideas, and then we can roll them out on the real world bench if we need to really prove a point. But yeah, so that's how all this works. The equipment cost for this is basically possible because of the Patreon donations and the GN store over the last couple of years, because we've got extra content, on patreon.com/gamersnexus if you want to support there. There's the Discord you can join, and then the store, obviously we sell shirts, or, well, we didn't make money on this one, but mod mats or the other shirts. And so that funds this. The cost, I haven't like actually added it up directly, but I think it's going to be about, I think for the dummy heaters plus the power supplies, we should be, let's see, I think we should be at about almost $10,000 plus or minus $1,000, and that's not counting some of the other stuff on the table here that I also had to set up for this. But so yeah, to really get this going, it's about 10 grand basically, but it's going to allow us to have, as far as I'm aware, the most accurate CPU cooler tests on YouTube, and maybe in written articles as well. So that's what we're pushing for, but everything works really nicely. I like the physical tool side of things rather than relying on software and BIOS and all this stuff that's inaccurate and just screws your numbers all the time. And then we can change the, I guess I'll do a quick demo of this. We can change the fan RPM too very easily. So if I wanted to do this by a non-PWM fan, this screen would not be relevant. We'd be running with a 3-pin instead, and then I would control over here with the dials. So we would use these dials to adjust the voltage, and you just set the current limit to whatever it is. The fan will pull what it wants, but set the voltage, and that would be your control for a 3-pin. For a 4-pin, because it's got a, we want 12 volts to it all the time. They're not happy if you don't do that. We could drop the speeds to, let's say, 50, which would probably bring us to about 800 to maybe 840 RPM. So I'm going to drop that to 50% symmetry. And we should already have an RPM drop. So if we go to scope, and then we calculate 28-ish point something, let's just call it 1.5, times 30, 844. And then let's just validate that math to make sure I didn't do anything wrong. 844, 849, 852. I mean, oh, oops, I just pointed it right at the sensor. Yeah, 850, 850, 850, 849. So that's pretty damn good. It's like, basically what you're seeing is everything validates everything else. So there's always two numbers, at least, for one value, which means we can very quickly see if something's wrong in the testing. But I don't know, it took me like over a year to get to setting up the PCB and the O-scope and everything for the fan testing. At the end of the day, it took me an hour and a half to do. And I just had to get on the phone with someone who could help guide me through some of the processes, but it took us over a year to arrange that. And then this other stuff took a couple days to set up because we were motivated to do it. So that's gonna be it for this extra video. Subscribe to this channel for more stuff like this, or some extra footage. I mean, there's everything from cat B-roll to biking here. Or you can go to patreon.com/gamersnexus to get access to the behind the scenes videos that are set to unlisted for Patreon backers, and you can grab that there. Thanks for supporting us in these endeavors. This stuff's already rolling, so the methodology video should be live by the time this is up. So you can check that out for the more detailed methodology on the physical, actual computer on the other side of the room, not this stuff. And then we should have a cooler review, probably of the A500 live, either when this goes up or within 2 days of it going up. So check for all that. Thanks for watching. I'll see you all next time.